Hello everyone, today I am going to discuss bearing capacity and foundation chapter, or in this lecture I am going to discuss effect of water table and shape of footing on bearing capacity of soil. So how this water table and shape of footing affect the bearing capacity of soil. So in the previous lecture we have discussed how we can calculate the bearing capacity of a soil, how we can calculate the ultimate bearing capacity of soil, and by calculating of ultimate bearing capacity of soil, we can calculate the net bearing capacity of soil or net safe bearing capacity of soil by assuming or by taking some factor of safety. So we have discussed the formula which was derived or which was discussed, which was given by the Terzaghi. So I will continue this lecture. So effect of water table on the bearing capacity of soil. So there is a 2-3 case. Okay. So I will discuss the 2 case, and you know that whatever the bearing capacity of soil we have calculated in the previous lecture. So water table was at a great depth. Means water table is at great depth from the base of the footing or of the footing level or from the footing level. So in this case we are going to discuss that if water table are above the base of the footing, then what will happen? If the water table is at the base of the footing, then what will happen? If the water table is just below the base of the footing at some small depth from the base of the footing, so what will result will effect? What effect will come in the ultimate bearing capacity of soil? So case 1, water table located above the base of the footing. So in this figure you can see water table is given by a dotted line or by a horizontal dotted line, and depth of water table from the ground surface is denoted by dW, depth of water table from the ground surface, and water table height from the base of the footing is mentioned by A distance, by A, right? So by figure or by denotation of the distance from the ground surface and base of the footing, you can say the depth of foundation is equal to depth of water table from the ground surface plus depth of water table from the base of the footing. So we can write dF is equal to dW plus A. So effect surcharge. So what surcharge will affect? So we can write Q is equal to dW gamma plus A gamma dash. Surcharge, what is the surcharge? Means you are calculating the bearing capacity and whatever the pressure will come at the base of the footing. So what you can write? What will the surcharge? So surcharge we can write कि water, those soil which are resting above the base of the footing, in what condition? So you can see the soil which is above the water table is in different condition. There is no water, right? And soil which is below the water table and above the base of the footing, those are in submerged condition. So we can write surcharge is equal to depth of water into gamma. Gamma is here the gamma is a bulk density of soil. Here the gamma is bulk density of soil. Now we can add what are the soil which is in submerged condition. So their height is A. So A into gamma dash. Here the gamma dash is submerged unit weight of soil. So now we can calculate, we can put the value of A is equal to dF minus dW. I told you dF is equal to dW plus A. By figure you can understand this. So by putting the value of A is equal to dF minus dW, so this result will come gamma dash into gamma dF plus gamma minus gamma dash into dW. So according to the Terzaghi theory, we can write ultimate bearing capacity for the soil C dash NC plus Q NQ plus 0.5 gamma B NQ. Right. Here the Q is the surcharge, or if we can say effective surcharge. So we can put the value of Q, and what is the Q we have we have written in the second equation. So now we can put the surcharge value of Q in this Terzaghi theory or Terzaghi equation. So you can get this equation. So now if the dW will take the 0, dW will take the 0, it means water table at the surface. Water table at the surface. Water table at the surface, it means dF is equal to A and dW will equal to 0. So after putting the value of dW is equal to 0 in the above equation, what we can get? We can get this result. QU is equal to Cn, C dash Nc plus gamma dash dF NQ plus 0.5 gamma dash B NQ. You can try, you will get this same result, right? So you can get this equation after putting the value of dW. So now you can remember, you can memorize this equation. So this equation is valid for what? This equation is valid for when the water table is the ground surface. When the water table is at the ground surface. Now if A is equal to 0, A is equal to 0 means water table goes down at the base of the footing. In this case, dF is equal to dW, where A is equal to 0, means water table at the base of the footing. Right. So after putting the value of A is equal to 0, you can get this relation. Q is equal to C dash Nc plus gamma and dF NQ plus 0.5 gamma dash B N gamma. So now in this equation you can remember when this equation is valid for the equation was valid for when the water table at the base of the footing. Second condition, when the water table located at the depth B below the base. By deriving the formula for the ultimate bearing capacity for the Terzaghi theory, we have taken the assumption that water table is at the great depth, at a very great depth, right? So now here B is very small as compared to great depth, like not infinity. Here is some value, some small value. So you can in this figure you can see the water table is at the depth of B distance from the base of the footing. Depth of foundation dF is given. So what will happen? See, in the formula of Terzaghi bearing capacity theory, the first term C dash Nc due to the cohesion, second term is due to the NQ due to the surcharge, third term due to the weight of the soil. Weight of the soil just below the base of the footing, just below the footing or immediately beneath the footing, right? So in this case, what will happen? This water table is B distance from the base of the footing. So it will not affect the cohesion properties. It will not affect the cohesion term, right? It will not affect the surcharge also. So the first term C dash Nc and Q will be the same. Are you getting a point? It will affect the third term, and third term came from weight of soil just beneath the base of the footing, or just beneath the footing, or immediately beneath the footing. Are you getting a point? So in the third term, you will see there is a 0.5 gamma B N gamma. N gamma depends upon the phi and shear strength parameter of soil. Okay, B the width of the footing, 0.5 the numerical value, so it will affect only the gamma. So gamma, what gamma we will take? We will take the gamma surcharge, or we will take the gamma of bulk unit weight or saturated. What we will take? So Terzaghi has suggested, after conducting so many experiments, so he has suggested some empirical relation, some relation. So by using that, we can calculate the ultimate bearing capacity in the case where the water table is at some depth below the base of the footing. So that relation is in this equation. See, in this case, second equation, gamma is mentioned by the gamma bar. Gamma bar, it means, in the gamma bar is mentioned. So gamma bar you can calculate by using gamma submerged, in submerged unit weight of soil, or from the bulk density of soil. And so by using this relation, you can calculate the value of gamma bar, right? See, this gamma bar will be always, we have to add in this case when the water table is at some depth from the base of the footing, right? Where the small b is the water table, b distance from the base of the footing, where the capital B is the width of the footing. When we'll take the b is equal to 0, so it will become a previous case when the water table is at the base of the footing. So by putting the value of b is equal to 0, gamma bar will be equal to gamma dash will be equal to submerged unit weight. So by putting the value v is equal to 0, or when the water table at the base of the footing, this QU, this 0.5 gamma become a submerged. So we can write 0.5 gamma submerged or gamma dash B and gamma. So this is the final equation or final formula when the water table at the base of the footing. Are you getting my point? When B is equal to B, when the water table at the same depth of water table at the below the base of the footing is the same is equal to the width of the footing, width of the foundation. So putting the value of B is equal to B, say gamma bar will become a gamma. Here the gamma is bulk unit weight. So when the water table at a B, capital B distance from the weight from the base of the footing, so you can take the gamma bar is equal to the bulk unit weight of soil. Or in this case, when the depth of water table from the base of the footing is greater than width of the footing, so there is no effect on the bearing capacity of soil. So it means whatever you get the relation for the B is equal to B, same relation will apply when the B greater than equal to B. Like in the case of gamma dash, you have to take the bulk unit weight of soil. Right? Are you very clear about it? I think there is no confusion when the water table at the ground surface. So what we will, how we can calculate the ultimate bearing capacity of soil when the water table at the base of the footing. So how we can calculate what formula we can use to calculate the bearing capacity of soil? If the water table at some depth from the base of the footing, so what formula we can use to calculate the ultimate bearing capacity of soil? Right. So let's discuss some numerical problem so that whatever we have discussed, we will be more clear about it. We can understand better by solving some numerical problem. So finally, for the square footing, so this whatever the relation we have discussed, this is the value for the strip footing. By deriving the formula of bearing capacity of soil, by deriving the formula according to the Terzaghi theory, we have taken the assumption that foundation is a strip foundation. Right? So all this formula, whatever I have discussed in the case 1, case 2, that is valid for the strip footing. So now, if the footing is square, if the foundation shape of footing is square, so we can use this formula. In the other book, they have written 1.3, but now I am taking the 1.2 C-NC, right? So for the square footing, we can use this formula. For the circular footing, we can use this formula. So at the place of 0.4 in the case of square footing, in the case of circular footing, 0.3 gamma B and gamma. So the first numerical, we have a 3 meter square footing is located in a dense sand at a depth of 2 meter. Determine the ultimate bearing capacity for the following water table position at the ground surface, at the footing level, and at 1 meter below the footing. The moist unit weight or bulk unit weight of sand above the water table is 18 kN per meter cube, and the saturated unit weight is 20 kN per meter cube. Unit weight of water is 10 kN per meter cube, phi, that is angle of resistance, angle of internal friction of a soil, 35 degree. C is 0, NQ for 35 degrees 33 and N gamma is 34. So we have to calculate the ultimate bearing capacity of soil for the different water table position. So let's discuss the first case, when the water table at the ground surface. So in the figure, it is mentioned that width of the footing is 3 meter, depth of foundation is 2 meter, water table is at the ground surface. So we have this formula for the square footing. So when the water table at the ground surface, we will take the gamma dash at the place of gamma bar. So rest we have, just put the value. So by putting the value of C is equal to 0, the first expression, the 1.2 C dash NC will be nullified, we can neglect, and that will be 0. So second expression, gamma dash dF NQ. So gamma dash, that is submerged unit weight. So we can calculate saturated density minus that water unit weight of water, we can get the submerged unit weight of soil. So 20 minus 10, we can get the submerged unit weight. 2 dF, depth of water, depth of foundation is 2 meter, and Q, so put all these value and we can get the result. QU, ultimate bearing capacity for the soil for the first condition, like water table at the ground surface. So we got the 1068 kilonewton per meter square. For the second case, when the water table at the footing level, in the figure, it is mentioned that water table at the base of the footing. So for the square footing, we have this formula. So what will happen? See, in the first term, it will not change. The second term, that is due to surcharge, means surcharge will change. In the first case, surcharge was submerged. Gamma dash dF NQ means those soil which is above the base of the footing was in submerged condition. But in this case, those soil which is above the base of the footing, that is not in submerged condition. That is in bulk condition, like moist condition. There is no water, right? In the third term, is due to the weight of the soil which is below the base of the footing, which is immediately beneath the base of the footing. So that is water table at the base of the footing, means that is in the submerged condition. So in the third expression, gamma will be gamma dash. Right? So put all these value. Like first expression will be 0 because C is 0. Dense sand means cohesionless soil is there. So by putting all these value, we can get the result 1596 kilonewton per meter square. Right? Third case, water table at 1 meter below the footing. 1 meter below the footing. This 1 meter is given a small b. This 1 meter is given small b. So in this figure, you can see water table is 1 meter below the base of the footing. So for the square footing, we have this formula. So in this formula, first expression is due to cohesion, second expression is due to surcharge. So in this case, surcharge, whatever the soil which is above the base of the footing, that is not in submerged condition. So that will, gamma will be gamma, bulk unit weight of soil. Third term, we will use the gamma bar, right? Because in this case, we cannot use, we don't know that what is the depth, up to what depth the soil is saturated and up to what depth the soil is not saturated, right? So we have this relation in this last equation, only we have to calculate the gamma. So we have the gamma dash, that is 20 minus 10, plus small b we have 1 meter, capital B we have 3 meter. Bulk unit weight we have, and then we can calculate the gamma bar. Got bulk unit weight we have 18 kilonewton per meter cube. So we have all these value. So we can put this in this equation, whatever equation is given in the third case. See, this is the third case, evidence case 2. No, this will be case 3, right? Okay. So we got the value of 1704.94 kN per meter square. 1704.94 kN per meter square. You can write this question and try to solve by yourself. You will get the idea like how we can calculate and how we are doing. See, so in the formula and the bearing capacity of soil, you will see that there is a three expression. First expression due to cohesion, second expression due to surcharge, third expression due to weight of soil that is beneath the base of the footing. So whenever the water table is changing, so the first expression is not changing. Expression is changing, the second expression or third expression means surcharge, whatever the expression due to surcharge or whatever the expression due to the weight of the soil which is beneath the base of the footing. So you have to see that condition. Like if water table is above the base of the footing, then surcharge will affect. If the water table is below the base of the footing, the third case, which is weight of soil which is beneath the footing or below the footing, that will affect, right? Next question, we have a square footing located at a depth of 1.5 meter below the ground surface carries a column load of 150 kilonewton. The soil is submerged having a unit weight of 11 kN per meter cube and an angle of shearing resistance 30 degree. Find the size of the footing using the Terzaghi theory. If C is equal to 0, factor of safety is 3, for phi 30 degree and Q is 10 and gamma is 6. So we have to calculate size of the footing. And here the footing, the shape of footing is square, right? We have to use the Terzaghi theory. So in this figure you can understand that whatever the load is coming 150 on the column and depth of the foundation is 1.5 meter. Submerged unit weight is given 11. So all the data we have. So we can calculate whatever the pressure is developed at the base of the footing. So suppose, and we can assume that width of the footing is capital B. So we can write the area of base of footing. That will be B square because the foundation, shape of foundation is square. So we can write net pressure which is developed by the load which is coming on the column on the footing. So pressure at the base is, we can write Q by A, load by area. So load we have 150 and we can write by B square. See, 150 is in the kilonewton, in the form of kilonewton, and B square suppose in the meter. So this 150 is the expression of kilonewton per meter square. Now we can calculate ultimate bearing capacity in terms of B by using the Terzaghi theory. So according to the Terzaghi bearing capacity theory, we can write this equation for the square footing. In this case, water table is the ground surface, means surcharge will affect and third expression also will affect due to the weight of the soil. So we can putting the value of C, the first expression C is equal to 0, first expression will be nullified. Second expression we can calculate. See, in this question, effective unit weight is given. Soil is submerged having effective unit weight. It means it is given the gamma dash. It is given the submerged unit weight of soil. Depth of foundation we have 1.5. NQ we have, for 30 degree we have 10. 0.4 into gamma dash we have 11, B that is unknown, and gamma is 6. So we can write ultimate bearing capacity in terms of B. Now we can calculate the net ultimate bearing capacity of soil. So how we can calculate? We can calculate by using the relation or by subtracting the overburden pressure from the ultimate bearing capacity. Or in this case, overburden pressure will be 1.5 into 11. Depth of foundation 1.5 and soil is in the submerged condition, so 1.5 into 11. So we can get the 148.5 plus 26.4 B. Now we can calculate the QNS, net safe bearing capacity of a soil. So by using factor of safety 3, we can calculate this value, that is 49.5 plus 8.8B. See, for safe foundation, for design of safe foundation, always whatever the pressure develop at the base of the footing, that should be less than or equal to net safe bearing pressure per soil. So in this case, Qn will be less than or equal to from the QNS. So we have Qn 150 by B square less than or equal to whatever we have again we have get for QNS. So in this equation only B is unknown. So by solving this equation, we can get the B equal to 1.6 meter. It will come around 1.54, but approximately we can write 1.6 meter. So size of the footing will be 1.6 into 1.6 in the form of a square, in the shape of a square, right? So in this question, the load was given and we have to calculate the size of the footing. So in the real life problems you will see when you will go to the field, you have to design the foundation. So by conducting the test, we have the bearing capacity of soil, we have the QNS value by assuming some factor of safety. So we do the same procedure, like we already designed what load will come from the superstructure, and by using that load we can design this foundation. Are you getting my point? Okay. So these are the references that I have taken to make this to make the PPT or record this lecture. Thank you. In the next lecture, I will discuss the plate load test, and from the next lecture, I will discuss the next unit also. Thank you.